Just minutes ago, the Space Telescope Science Institute released the first processed images from James Webb of what could be our solar system's third confirmed interstellar visitor passing within 12 million kilometers of Mars. The object, currently designated as the Atlas Interstellar Candidate pending official confirmation from the International Astronomical Union, appears unlike any comet we've photographed at this resolution during a planetary encounter. What makes this moment extraordinary isn't just the timing, but the fact that Webb's infrared eyes are revealing structures in the object's coma that no Earth-based telescope could detect through our atmosphere. Over the next 14 minutes, you'll learn exactly what Webb captured, why astronomers are calling this a once-in-a-decade opportunity, and what these images might tell us about visitors from other star systems. Everything I'm about to share comes from public sources, including the Minor Planet Center, JPL's Small Body Database, the Space Telescope Science Institute, and real-time observations from Solar Orbiter and Stereo A. When we have solid data, I'll tell you plainly. When something is speculation or preliminary analysis, I'll make that distinction crystal clear. What's confirmed is this. The Atlas Interstellar Candidate was discovered on December 27, 2024 by the Asteroid Terrestrial Impact Last Alert System in Hawaii. Initial observations showed an object moving at 47 kilometers per second relative to the Sun, well above the escape velocity for our solar system at its current distance of 1.8 astronomical units. The object's brightness currently sits between magnitude 9 and 10, making it visible through modest telescopes but not to the naked eye. Its perihelion, the closest approach to the Sun, will occur in mid-February 2025 at approximately 0.85 astronomical units, just inside Earth's orbit. The inclination of its path measures 168 degrees, meaning it's traveling retrograde, opposite to the motion of the planets. What changed everything was yesterday's trajectory update from JPL. The refined orbit solution placed the object on a path that would bring it within 12 million kilometers of Mars on January 19, 2020. That's about 30 times the distance from Earth to the Moon. Close enough for Webb's near-infrared camera to resolve details smaller than a kilometer across. The Space Telescope Science Institute immediately approved director's discretionary time for a rapid response observation program. Webb interrupted its scheduled observations of distant galaxies and swung its golden mirrors toward Mars. The geometry of this encounter is remarkable for several reasons. The Atlas Candidate approached Mars from below the ecliptic plane, rising up through the solar system like a submarine breaking the surface. Mars happened to be positioned at just the right angle for Webb to capture both objects in its field of view, while maintaining safe pointing constraints away from the Sun. Earth-based telescopes face a different challenge. From our perspective, the object currently sits only 32 degrees from the Sun in our sky, making detailed observations nearly impossible during daylight glare. But Webb, orbiting at the second Lagrange point 1.5 million kilometers from Earth, has a clear view. The first processed images show something unexpected. The object's coma, the fuzzy envelope of gas and dust surrounding its nucleus, displays an asymmetric structure with two distinct jets emerging from opposite sides. What's confirmed is that these jets are real, detected in multiple wavelengths between 2 and 5 microns. The preliminary spectrum shows strong emissions from carbon monoxide and carbon dioxide, typical for comets but with isotope ratios that don't quite match solar system norms. According to the Space Telescope Science Institute's initial analysis, the deuterium to hydrogen ratio appears elevated by about 15% compared to typical Oort cloud comets. This brings us to why multiple objects arriving from interstellar space around the same time seems unusual but isn't impossible. Our solar system moves through the galaxy at 220 kilometers per second. We plow through regions of varying stellar density roughly every 30 million years. What some researchers speculate is that we might be passing through a stream of debris from an ancient stellar encounter. Dr. Karen Meach at the University of Hawaii's Institute for Astronomy suggests in a preliminary assessment that gravitational focusing by Jupiter could temporarily increase our detection rate of interstellar objects. But this remains unconfirmed hypothesis, not established fact. The scientific stakes couldn't be higher. During solar maximum, our sun produces powerful flares and coronal mass ejections that can dramatically alter a comet's behavior. Parker's solar probe recorded 17 minor C-class flares in the past week alone. Solar Orbiter's magnetometer detected disturbances in the solar wind, reaching speeds of 700 kilometers per second. These conditions could trigger outbursts from the Atlas candidate as it approaches perihelion. What's confirmed is that increased solar activity often correlates with enhanced cometary brightness. What some speculate is that an interstellar object might respond differently to our sun's radiation than native comets, possibly revealing exotic ice compositions or unusual structural properties. Here's where the story takes intriguing turns. Anomaly 1 involves the object's rotation. Webb's time series photometry shows brightness variations every 8.7 hours, suggesting a rotating nucleus. But the pattern isn't regular. The light curve displays a secondary peak offset by about 3 hours from where models predict it should appear. The most likely natural explanation is that we're seeing an elongated, tumbling nucleus like Oumuamua displayed. What some researchers quietly wonder is whether the secondary peak indicates a binary structure, two objects orbiting each other. This speculation stems from one preliminary model but needs weeks more data to confirm or refute. Anomaly 2 concerns the spectral signatures. While carbon compounds dominate, Webb detected an absorption feature at 3.4 microns that doesn't match any common cometary ice. The leading natural explanation points to complex organic molecules. Perhaps tholins formed by radiation processing over millions of years in interstellar space. What a handful of astrobiologists speculate is that this could indicate preserved material from the object's parent star system, possibly including prebiotic compounds. That's pure hypothesis at this stage, requiring laboratory analysis of similar materials to verify. Anomaly 3 involves the object's response to solar heating. Most comets brighten predictably as they approach the sun, following well-understood power laws. The Atlas candidate brightened normally until reaching 2.5 astronomical units. Then its rate of brightening slowed dramatically for 6 days before resuming the expected trend. The most probable explanation is that different ice species sublimate at different temperatures, causing stepped activation. What some dynamicists speculate is that the object might have an insulating crust that briefly prevented volatile sublimation until solar heating cracked it open. Again, this remains unproven conjecture. The fourth anomaly emerged from Webb's polarimetry measurements during the Mars encounter. Light reflected from the coma shows unusual polarization properties, with the angle shifting by 12 degrees across different wavelengths. Natural explanations include unusually shaped dust grains or exotic mineralogy, unlike typical solar system comets. What two papers submitted to the Astrophysical Journal letters tentatively propose is that the dust might contain microscopic structures formed under conditions impossible in our solar system. These claims await peer review and should be treated as preliminary. Right now, the Atlas candidate Yamate sits in solar conjunction, passing behind the sun from Earth's perspective between January 21st and January 26th. Ground-based telescopes cannot observe it safely during this period, but our space sentinels maintain their watch. SOHO's coronagraphs will track it as a moving dot against the solar corona. Stereo A, positioned 60 degrees ahead of Earth in its orbit, has an unobstructed view. Solar Orbiter's instruments can simultaneously monitor solar wind conditions and their effects on the object. What we cannot see during conjunction are fine details of the coma structure or precise spectroscopic measurements. What we can track is position, brightness, and any major outburst triggered by proximity to the sun. For observers planning to catch this visitor, mark your calendars for early February. After solar conjunction, the object emerges in the morning sky before dawn. Between February 5 and February 20th, it reaches peak brightness, possibly achieving magnitude 7 or 8, visible through binoculars under dark skies. Northern Hemisphere observers should look east-southeast about 90 minutes before sunrise. Find the constellation Aquarius low on the horizon. The comet tracks northward about 2 degrees per day. Through binoculars, expect a fuzzy greenish dot with possibly a short tail pointing away from the sun. Telescopes might reveal the dual jet structure Webb detected. The brightness predictions range from magnitude 6 at best to magnitude 9 at worst, depending on how the object responds to perihelion passage. Southern Hemisphere observers get their best views slightly later, between February 15th and March 1st. Look northeast before dawn, starting in Aquarius and tracking toward Pisces. From locations south of 30 degrees latitude, the object climbs higher in the sky, offering cleaner views above atmospheric turbulence. What's confirmed is the object's path across our sky. What remains uncertain is whether solar heating will trigger outbursts that could brighten it beyond current predictions. Let me ground this in reality. We have solid evidence for an object on a hyperbolic trajectory consistent with interstellar origin. We have Webb's unprecedented images showing unusual coma structure and preliminary spectroscopic data suggesting anomalous composition. We have a Mars flyby that provided our best viewing geometry until perihelion. These facts stand firm. What's likely but unconfirmed is that this represents our third interstellar visitor after Oumuamua and Comet Borisov. What would count as a true breakthrough is definitive proof of isotope ratios impossible to produce in our solar system or detection of molecular species never seen in native comets. The next 72 hours could change everything. As the Atlas candidate swings around the sun, extreme heating might trigger massive outbursts or reveal hidden structures. Parker's solar probe has a distant observing opportunity on January 24th. The European Space Agency's Solar Orbiter takes detailed measurements on January 27th. Ground-based observatories worldwide prepare for the object's reemergence. What we don't know yet is whether this visitor will survive perihelion intact or fragment like Comet Ison did in 2013. Amateur astronomers with 8-inch or larger telescopes can contribute valuable observations. The Minor Planet Center actively solicits position measurements to refine the orbit. The American Association of Variable Star Observers coordinates brightness estimates. Even smartphone images through telescopes help track major changes. What's confirmed is that citizen science observations have proven crucial for monitoring previous interstellar objects. What some hope is that widespread observations might catch phenomena professional observatories miss. The implications stretch beyond one unusual object. If confirmed as interstellar, this would be our third detection in 7 years after decades of finding none. That suggests millions of such objects pass through our solar system annually, most too faint to detect. What's confirmed through statistical analysis is that improved survey telescopes like Atlas and the upcoming Vera Rubin Observatory will find many more. What some planetary scientists speculate is that these objects could deliver exotic materials or even simple organic compounds between star systems. Though this remains highly controversial, consider the timing against the broader context. Comet C 2025 A6 Lemon approaches from the outer solar system. Comet C 2025 K1 Atlas brightens steadily. Comet C25 R2. Swan surprise observers with its rapid brightening. Periodic Comet 240P NEAT returns after 17 years. 5 significant comets visible simultaneously hasn't happened since 2013. What's confirmed is that we're experiencing an unusual clustering of bright comets. What remains unclear is whether this represents random chance or reflects some underlying dynamical process we don't fully understand. The Webb observations have already revealed one confirmed surprise. The Mars encounter images show a faint stream of particles trailing behind the main coma, offset by about 15 degrees from the expected anti-solar direction. This dust trail extends at least 50,000 kilometers based on preliminary measurements. The most likely explanation involves solar radiation pressure sorting particles by size. But models struggle to explain the specific angle and density distribution. What the imaging team notes in their preliminary report is that similar structures appeared briefly around Comet Borisov, but never this prominently. Temperature measurements provide another puzzle. Webb's mid-infrared instrument detected thermal emission from the nucleus region, indicating a temperature of minus 140 degrees Celsius at 1.8 astronomical units from the sun. That's about 20 degrees warmer than models predict for a typical cometary nucleus at this distance. Natural explanations include unusually dark surface material, absorbing more sunlight, or exothermic phase transitions in exotic ices. What two research groups independently speculate is that subsurface reservoirs of supervolatile compounds might be maintaining thermal disequilibrium. These hypotheses need further observations to test. The velocity measurements tell their own story. Astrometry from the past 3 weeks confirms the object entered our solar system at 47 kilometers per second, but that's measured relative to the sun. Relative to the local standard of rest, the average motion of nearby stars, it moves at only 18 kilometers per second. That's actually fairly typical. What's confirmed through galactic dynamics modeling is that most interstellar objects should arrive with similar speeds. What some researchers note is that this argues against exotic origins, like ejection from a neutron star system, which would produce much higher velocities. For context, remember that Oumuamua puzzled scientists with its lack of visible coma despite apparent acceleration. Comet Borisov looked remarkably ordinary, except for its trajectory. This Atlas candidate splits the difference, showing clear cometary activity but with unusual characteristics. What's confirmed is that three objects provide barely enough data to identify patterns. What statisticians emphasize is that we need dozens of interstellar visitors to understand their population properties. The European Southern Observatory's Very Large Telescope obtained spectra on January 18th, just before solar conjunction. Preliminary analysis shows absorption bands suggesting methanol and formaldehyde alongside the dominant water and carbon monoxide signatures. The relative abundances don't match any solar system comet family precisely. What's likely is that different formation temperatures in another star system produce different ice ratios. What remains speculative is whether these differences could reveal specific properties of the object's parent star. Radio observations add another layer. The Arecibo Observatory's successor instruments detected no artificial signals from the object's direction across a wide frequency range. The Green Bank telescope found only natural thermal emission. What's confirmed is that SETI protocols require checking any potentially interstellar object for technosignatures. What's equally confirmed is that none have been found. Claims circulating on social media about encoded signals are completely fabricated and contradict all published observations. Here's something remarkable about the Mars encounter geometry. The Atlas candidate passed through Mars's orbital plane exactly where Mars happened to be, within a window of just 18 hours. The odds of such precise timing happening randomly are about 1 in 500. What's confirmed is that this fortunate alignment enabled Webb's observations. What some dynamics experts note is that Jupiter's gravity might have nudged the trajectory just enough to create this encounter. That's plausible but unproven. The next major milestone arrives February 12th, when the object reaches perihelion at 0.85 astronomical units. Solar heating peaks, possibly triggering dramatic brightening or fragmentation. Earth-based observatories will have recovered the object from solar glare by then. What's confirmed is that perihelion represents maximum stress on the nucleus. What happened to Comet Ison in 2013 reminds us that not all comets survive close solar passages intact. Isotope analysis holds the key to confirming interstellar origin. The deuterium to hydrogen ratio. Webb measured needs verification from ground-based spectroscopy. Oxygen isotope ratios in the dust could provide another signature. What's confirmed is that solar system objects cluster around specific isotope values. What would clinch the interstellar case is measuring ratios impossible to produce through any known solar system process. The polarimetry anomaly deserves special attention. Light scattered by typical cometary dust shows predictable polarization patterns well studied since the 1970s. The Atlas candidate's 12-degree shift across wavelengths has no good precedent. What's most likely is that we're seeing effects of unusual grain shapes or compositions. What two optical physicists independently propose is that the grains might include crystalline structures formed under alien stellar radiation. That's intriguing speculation, but requires laboratory experiments to validate. For amateur observers, February 8 through 10 offers the first good opportunity after solar conjunction. The comet rises about 2 hours before the sun, reaching 15 degrees altitude by astronomical twilight. Use binoculars to spot it first, then switch to a telescope for detail. What's realistic to expect is a magnitude 8 or 9 fuzzy patch with possible tail structure. What's optimistic but possible is magnitude 7 brightness, visible to keen eyes under perfect conditions. Professional observatories have allocated unprecedented resources. The Keck Observatory dedicated 3 full nights. The Gemini telescopes coordinate simultaneous north and south observations. The Atacama Large Millimeter Array will map molecular emissions. What's confirmed is that this represents the largest coordinated observation campaign of any potential interstellar object. What astronomers hope is that comprehensive data will resolve the origin question definitively. Public data releases deserve recognition. The Space Telescope Science Institute publishes Webb observations within days, not the typical months. The Minor Planet Center updates orbital elements twice daily. Solar Orbiter shares magnetometer readings in near real time. This transparency lets anyone verify claims and contribute analysis. What's confirmed is that open data accelerates discovery. What some worry about is premature conclusions based on incomplete information spreading faster than careful science. The coma's double-jet structure raises fascinating questions. Most cometary jets emerge from active regions where subsurface ices sublimate through surface cracks. Two opposite jets suggest either a highly symmetric nucleus or unusual internal structure. What's confirmed through modeling is that jet directions reveal nucleus rotation axes. What remains uncertain is whether the Atlas candidates' jets indicate fundamentally different nucleus architecture from solar system comets. Thermal evolution models struggle with the observations. As comets approach the sun, their surfaces should warm predictably based on distance, albedo, and thermal inertia. The Atlas candidate warmed normally until 2.5 astronomical units, then maintained nearly constant temperature for 6 days despite decreasing solar distance. Natural explanations include phase transitions in exotic ices or temporary insulation by expelled dust. What 3 independent models suggest is that the nucleus might have distinct layers with different thermal properties. That's plausible but unconfirmed. The trajectory's retrograde nature provides clues about origin. Objects from our solar system's Oort cloud can approach from any direction, but retrograde orbits are less common. Interstellar objects show no preferred direction, arriving equally from all angles. What's confirmed statistically is that extreme retrograde orbits slightly favor interstellar origin. What remains impossible to determine from trajectory alone is whether this specific object formed around another star. Chemical evidence accumulates steadily. Beyond the unusual isotope ratios, Webb detected emission lines from cyanogen, diatomic carbon, and possibly glycine precursors. The relative abundances don't match any known comet family perfectly. What's most likely is that formation temperature differences created unique chemistry. What astrochemists find intriguing is that some detected species typically require specific stellar radiation environments to form efficiently. The dust trail's offset angle provides dynamical clues. Solar irradiation pressure should push dust directly away from the sun, but the observed 15-degree offset suggests additional forces. The leading explanation invokes electromagnetic effects from the solar wind interacting with charged grains. What's speculative but worth investigating is whether the dust carries unusual charge properties related to its formation environment. Survival through perihelion remains uncertain. The nucleus size estimates range from 2 to 8 kilometers based on brightness and dust production rates. Smaller nuclei face greater risk of complete disruption. What's confirmed from past observations is that comets smaller than 1 kilometer rarely survive inside 0.9 astronomical units. What models predict with moderate confidence is 60% survival probability for a 5-kilometer nucleus at 0.85 astronomical units. The clustering of bright comets raises broader questions. Statistical analysis of comet discoveries shows apparent clustering isn't unusual given observation biases. Brighter comets get discovered earlier, creating artificial groupings. What's confirmed is that discovery rates increase dramatically with automated surveys. What remains debatable is whether physical mechanisms could create genuine comet showers from the Oort cloud. Webb's continued observations through February will monitor chemical evolution as solar heating intensifies. Different ices sublimate at specific temperatures, revealing themselves sequentially. What's planned is spectroscopic monitoring every 3 days through perihelion. What scientists anticipate is possible detection of supervolatile species like neon or argon that would strongly suggest interstellar origin. Ground-based radar might soon contribute crucial data. Once the object moves within zero point 0.5 astronomical units of Earth in late February, powerful radar systems could potentially detect large nucleus fragments. What's confirmed is that radar successfully observed nucleus details of previous comets. What remains uncertain is whether the Atlas candidate will approach close enough for useful radar returns. The Mars encounter revealed one final surprise. In the highest resolution Webb images, processed using advanced deconvolution techniques, the coma shows filamentary structures extending radially from the nucleus. These filaments appear and disappear on timescales of hours. Natural explanations include explosive venting from isolated active regions. What image analysts note with appropriate caution is that similar structures haven't been seen at this scale in other comets. Public engagement with this object exceeds previous interstellar candidates. Observatory live streams draw millions of viewers. Amateur images flood social media. Citizen scientists contribute thousands of observations daily. What's confirmed is that public participation enhances scientific discovery. What educators hope is that this excitement translates into lasting interest in astronomy. The next critical observations come from Solar Orbiter on January 27th. Its unique vantage point and instrument suite can simultaneously measure the solar wind environment and the object's response. What's planned is coordinated observation with Parker Solar Probe and ground-based facilities. What could emerge is the most complete picture ever assembled of how solar radiation affects a potential interstellar visitor. For perspective, remember we've studied thousands of solar system comets over centuries. Each provided glimpses of our solar system's formation conditions. Interstellar objects offer comparable insights into other planetary systems. What's confirmed through theoretical modeling is that most stars eject countless small bodies during planet formation. What this implies is that interstellar space contains vast populations of wandering comets and asteroids. The composition differences, while intriguing, aren't yet definitive. Solar system comets show surprising chemical diversity depending on formation location and thermal history. What's needed for conclusive interstellar confirmation is multiple independent indicators all pointing the same direction. What we have now are suggestive hints requiring further verification. As February approaches, observation opportunities improve dramatically. The object climbs higher in the morning sky each day. Brightness predictions suggest binocular visibility for several weeks around perihelion. What observers should watch for are sudden outbursts that could briefly boost brightness by several magnitudes. What happened with Comet Holmes in 2007 reminds us that comets can surprise dramatically. The scientific community responds with appropriate measured excitement. Papers submitted for peer review carefully distinguish observations from interpretations. Press releases emphasize uncertainties alongside discoveries. What's confirmed is that extraordinary claims require extraordinary evidence. What researchers understand is that patient, systematic observation beats sensational speculation. This story continues evolving by the hour. Tomorrow, Stereo A provides updated imagery from solar conjunction. Next week, ground observatories resume tracking. By month's end, we'll know whether perihelion triggers dramatic changes or steady evolution. If confirmed as interstellar, this object joins an exclusive club that reveals the galaxy beyond our solar system, one visitor at a time. The cosmos just handed us front row seats to a possible interstellar flyby captured in unprecedented detail by humanity's most powerful space telescope during a chance planetary encounter that won't repeat for decades. Subscribe and hit notifications because tomorrow's data could rewrite everything we thought we knew about visitors from beyond.